Welcome to my channel. I'm Zhang Xu. Let's look at the problem 33 in chapter 23. Chapter 23 is about electric potentials. In this system, we can see we have a thin circular ring radius is R. The upside with the charge Q/2 uniformly distributed. The bottom half with the charge negative Q/2 uniformly distributed. So we need to find the value of electric potential at a point, a distance x, along the axis, right? So we consider this position is P at there. So first one, we look at the half part. We choose a small fraction of the charge dq, right? And then we can find the distance from this charge to the position is just a squared x squared plus r squared. Agree? Yes. Now, can you find the potential due to the dq? Yes, you can write the function at there. Right? The function is there. And the next one, we can see for the mirror symmetry, we can see at the bottom side, we have another charge, negative dq. Agree? Negative dq. And then, similarly, we can also write the potential at the position P. Look like this one. Right? And you can see if you add these two potential together, the answer is 0. Agree? So these two cancels. These two cancels. So that means in each small fraction of the dq, it has the corresponding mirror symmetry, negative dq. So this will make the potential at the position P just cancels. So in this way, the electric potential at the distance x at the position P is 0. Agree? Yes. The next one, what can you see about the electric field at a distance x along the axis? So now we can see, in this one, we can see, because this is a positive charge, right? So we choose a small fraction. We can see the electric field by this small fraction dq, right, as dE top. And then at the mirror symmetry, we can get another small fraction of charge, negative dq, and then we can write its electric field pointing to negative charge as dE bottoms, right? And then we can see for these two electric fields, the magnitude equals as dq over 4 pi epsilon naught r squared, and r is just the distance from the charge with the position P there. So we write it there, right? So it looks like we need to add these two vectors together to find the total electric field. So we project the electric field in the x component and the y component, right? So first one, we projected in x component. You can see this is angle theta, this is angle theta, and this is also angle theta, right? So this is angle theta. So project the dE top at x component as dE cosine theta, at the y component dE sine theta. Similarly, we can project the dE bottoms as dE cosine theta, dE sine theta. You can see at the x component, these two vector cancels, right? These two vector cancels. So at x component, the electric field is 0. At the y component, you can see pointing to negative y component. So we add the negative side there, and it's 2 times dE sine theta, right? Yes. Now we need to solve the EY. So it looks like first thing dE is given at there. We can input it inside. Next one, how can you find sine theta? So easy, right? This is a triangle. This is a triangle. So sine theta is just r over the squared x squared plus r squared, right? So this is how we get the sine theta. Now we input the sine theta inside. But you can see now when we input the d, we can get the function look like this one, right? The next one, how can you find the dq? dq, we can write it as the charge density times the distance. This is a small fraction, right? The length of this small fraction. Now the charge density, we can see for the upside. For the upside, we see the total charge is Q/2 divided by the length of the arc, pi times r. then times the small fraction length dl, right? So we input this dq inside. So now there we input the dq inside. We get function look like this one. Agree? And then simplify it. We can say it looks like this one. Now it looks like we just need to do the integral for the dl, so we can get ey. So you can see in this case we do the integral. We just consider the dl. If we just cut the small fraction, right? Just the half of the circle from the 0 to pi times r. From 0 to pi times r, this is half of the length of the half of the circle. So you can say 0 to pi r, and then after you do the integral, the function look like this one. This is the electric field density magnitude at the y component, and we know the x component is 0, so you can write the electric field density looks like this one, right? Thank you.